Well, let's take number 63. We want to find the pH when we have these two added together. Now, if you notice, this is a weak acid. That's why we have the Ka here. The fact that this has potassium, any group 1 metal in a salt means it's 100% soluble. So this is going to break down 100%. K positive and NO2 negative. Both aqueous. Okay? This is kind of going to break down into H positive plus NO2 negative. Now you can see the common ion here. Now because this is a single arrow reaction, that means all of this is going to break apart to give us 0.10 molar of this and 0.10 molar of this, because the stoichiometry is 1 to 1 to 1. Doesn't split up, it stays intact. This, however, is a weak acid, so we're going to lose X to the 0.15. We're going to gain X here, and we're going to gain X here. So, this is the one we're going to focus on. Okay? So this is going to be X times X. Excuse me. We'll just put this X to 4.5 times 10 to the negative 4. X times X in the numerator and 0.15 molar minus X for the denominator. Now I'm going to do something with this. I'm going to do this twice so that you can see another way of doing this other than what I'm doing right here. And you'll probably like to do it that way rather than what I'm doing right here. But let's continue on as if this is the only way to do it. Multiply both sides by 0.15 minus X. Alright, so I get 6.75 times 10 to the negative 5 minus 4.5 times 10 to the negative 4x equals x squared. Now I'm going to bring the x squared over, switch those two around, so I got the descending order of degrees of x. So that's negative x squared minus 4.5 times 10 to the negative 4x plus 6.75 equals 0. Whoa! We got the times 10 to the negative 5. That would not have been good. Times 10 to the negative 5 equals 0. Alright, good job, can't fail. So now, go to quad form. And negative 1 for A. Negative 4.5 E. Negative 4 for B, and 6.75 E, negative 5 for C, and the positive value you get for X here is 0.00799 moles per liter. Now, what does that X represent? Well, you can see right here. X represents H positive. So that's the concentration of H positive. Why is that important? Because that's how you find pH. pH is the negative log of H positive, which is that number right there. So I get second log, second answer. And I get 2.10. And there's your pH of the solution. Okay? That's one way to do it. Let's do that again, starting from right here, before I multiply both sides by 0.15 minus x. So I'm going to rewrite that below here, give a little pause there. So Ka, 4.5 times 10 to the negative 4 is equal to, and we had x squared over 0.15 minus x. Now, when we looked at the first problem, and we saw that there was a rather significant drop in the percentage of the amount that was associated, how much iron came off. There's a distinct possibility that we can simplify this problem. And so let's do this and compare what we would have gotten right here. We know that X is going to be extremely small in comparison to the 0.15. In this case, what we said here, that this is 0.008, which is about a 20th. If you were to divide that by 0.05 or 5%, that is going to be a small difference. So let's see how much it's going to change if I drop the minus X. Because if it's an insignificant quantity, then we can just go ahead and do that. It's not going to have an effect upon the overall, not much of one. It'll have a little bit. But let's see what happens when that takes place. Because I think you're going to like how this ends up happening. So we got X squared equals X, so multiply both sides by 0.15. So X squared is equal to 6.75 times 10 to the negative fourth. Okay? No, that's right. That's not right. That's negative fifth, actually. Yeah, negative fifth. So did I do that correctly up there? I believe I did. Yes. Okay. Now all you have to do is take the square root. We're going to use quad form. So now let's take the square root of 6.75 e negative 5, and let's see what we get for an answer. We get 0.00821. It's not exactly the same as that. Close. And I will tell you right now, the greater the disparity, the smaller the Ka, the more likely you should do it. So I would say that when you get to Ka's of 10 to the negative fifth and smaller, do it this way. All right? If you get it right around 10 to the negative fourth, you need to do it the way you did up there, because there is a bit of a difference enough. In fact, if I took the negative log of that, negative log second answer, we get 2.09. And the answer is 2.10. You probably could get away with doing that this way. So, but I think it's safer to wait until you get all the way to 10 to the negative fifth. And I think you will actually see that the same number comes up. So there's a slight difference, but so make sure it's 10 to the negative fifth. Okay, for this one right here. Now, this one doesn't jump out at you and say, wow, we got something in common here. But I think if you dissolve, not dissolve, they're both aqueous solutions. But if you write the aqueous solutions for this, you're going to get, we'll start off with, this is methylamine, which is a base now instead of an acid, NH2 plus H2O, which we think of again as HOH. And what's going to happen here is, because this is a base, the hydrogen is going to go to the nitrogen to form CH3 and H3 positive plus OH negative. Okay? Now, here's the thing. This is the conjugate acid. How can we tell? Because when you add water to it, these are the two products you get. And you can see that you have a common ion here. And the fact that it's a chloride means it's a salt. Now, it turns out that halogens as negative ions with conjugate acids of weak bases are 100% soluble as well. So in actuality, you could drop that Cl and make that just CH3 and H3 positive. So this becomes 0.15 molar CH3NH3. Okay, this is 0.10, so this would be 0.10. Now we put that down there, and it's going to be, and I got a single arrow, and I gotta tell you, I really screwed up on that one. That's a double arrow because that's a weak base, so that should not be a single arrow. So double arrow, that's actually a single arrow up there if you wrote the equation out for that. In fact, let's do that. If we have CH3, NH3, Cl plus H2O, that's a single arrow reaction because of that chlorine, which is the halogen there. And this is going to form CH3, NH3 positive plus Cl negative. And again, that's a spectator ion, and that's not going to do anything. But, there's always that big but. You have 0.15 molar of this, and it's a single arrow right there. That's all gone. That's 0.15 there, and that's 0.15 there. Of course, we don't care. This one right here, being a weak base, we're going to lose X here, we're going to gain X here, and we're going to gain X here. Okay? Now, we go ahead and notice that we have this common ion right here. So this is going to be, what did I say the KB for this was? 4.4? And the fact that it's a KB, that tells you you better get OH negative as one of your products, not H positive. H positive means you have an acid, so that's a Ka. KB tells you you need to be getting an OH negative in your reaction. So that's going to equal to X times X, which is X squared. Oh, sorry. It would have been had there not been that 0.15. So that's X plus 0.15 times X over 0.1 minus X.